We're going to discuss quantification today, in particular as a theoretical concept. A separate video will show you the discrete steps needed to perform a quantification. Before we continue, I want to focus on two concepts that I think are critical to keep in mind. This is based on work by Anna Romanovsky and Anna Stefan from back in the 1990s. That is analytic units and synthetic units. An analytic unit includes the raw data obtained from the instrument. In the case of X-ray fluorescence, this would be your spectrum. The synthetic unit is a transformation of that unit into a separate type of unit, a synthetic unit. This includes incorporating various assumptions, which could be anything from the type of material that's in the sample, other elements present, or even the matrix. A synthetic unit would be weight percent, or parts per million, for example, in most common XRF applications. The instrument doesn't produce weight percent or part per million data. Rather, it produces an analytic unit, the spectrum. A synthetic unit requires outside information. We're going to take some time and briefly review what X-ray fluorescence is so that we keep in mind what is happening from the ground up. Here's our atom. We have a nucleus in the center with both protons and neutrons. Protons have a positive charge, while neutrons have a neutral charge. Surrounding them is a cloud of electrons organized into discrete orbitals. You may recognize this as the Bohr model of the atom. Electrons have a negative charge. Here we see them as K in the K, L, and M shells. You can remember that as the Dutch Airlines Company. The other way to remember it is as MLK, or Martin Luther King. The thing to remember about electrons is that electrons hate other electrons. They have a negative charge and repulse each other. So thus, an electron has two goals: to be as close to the nucleus as possible and to be as far away from those other electrons. With X-ray fluorescence, we send in a photon with enough exciting energy to be absorbed by the electron. This energetic electron now has enough energy to leave the atom. It no longer has the same attraction to the nucleus as it did before. As a result, we see this electron leave its orbital. We now have a vacancy in the K orbital. This vacancy means that we can have any electron come in and then take its place. What happens at this point is that every electron in the atom moves to take this position, resulting in a temporary destabilization of the atom. The electrons jostle about until one finally manages to drop down in energy state and move into the open K orbital. Once this happens, that electron has crossed an energy boundary from a high energy state to a low energy state. And as a consequence of this energy change, we get a photon in exchange. This photon captures the energy difference between the L and K shell, which in turn is defined by the number of protons exerting an attractive force on those electrons. Each K-line emission is different for each element because each element has a different number of protons. Now, when this photon comes from the L orbital, we call it a K-alpha line. This happens most of the time since L is in such close proximity. However, a small fraction of the time, this donated electron can come from the M shell. In this case, we call it a K-beta line. In any case, one K-alpha photon is evidence for one atom, whereas one K-beta photon is evidence for still one atom. The number of alpha and beta peaks, or the height of the alpha and beta peaks, will give us a sense of how many atoms are in our sample. So here, for example, you see an example of several spectrum on top of each other. If you look at the iron peak, which is to the center right in this diagram, you see multiple spectra with different heights for the iron peak. The more iron atoms in the sample, the higher this peak becomes. Now, it's easy to think that the height of this directly corresponds to weight percent or parts per million, but as a hypothetical, if our bottommost purple line indicated 4 weight percent iron, and our topmost light blue/green line indicates 6% iron, we must remember that that's only percent iron. The other elements in the sample, whether it's silicon, calcium, or sulfur, also affect the relative percent of iron. If, for example, you had a large quantity of lead in the spectrum, the same number of atoms of iron would contribute proportionally less to the overall weight percent, regardless of if it's the same number of atoms or not. So it's important to remember that our analytic unit is a measure of the abundance of atoms. Our synthetic unit makes assumptions about all the other elements inside the sample. Here we see a similar diagram, but this time each spectrum is colored red. This is done because we're looking at essentially a calibration, a reference set spectrum. These are 26 mudrock standards, each with known concentrations for iron, calcium, etc. The height of the peak corresponds to how many atoms are present. Here, we're evaluating if we can quantify a set of Chinese porcelains using this calibration. To make this determination, I plot the spectra of the Chinese porcelain over the mudrock standards, and then I look to see if it fits. In general, for a calibration to work, the reference spectra must capture the highest and lowest possible concentration of each element. In this case, visually, it should have the mudrock standard should be both the highest peaks and the lowest peaks that we see. Here, I add the Chinese porcelain standards, and immediately you can see, for example, for calcium, potassium, and iron, all these different colored spectrum fit within the red maximum and minimum lines, indicating that this quantification would work. But look at manganese. With the case of manganese, we see a lot more of it, and because of it, that means that our calibration does not capture the full range of variation for manganese. Additional standards in this case would be needed. We'll return to this example once we've talked a little more in depth about what a calibration is and is not. So to move from abundance of atoms as reflected in the spectrum to weight percent or parts per million, we need a couple things. First, we need a standard with a given matrix. Second, we need mathematical models that translate those standards into something that we can analyze our sample with. So in this case, to the left, you see a set of reference standards. We obtain spectra from these reference standards to capture ideally the minimum and maximum of every element present. Then math happens, and then we produce what is called a calibration curve. This calibration curve is then used to articulate the variation we see in the photons of our sample into something quantitative, like weight percent or parts per million. Here is what is happening when we start using math. We specifically, for the tracer, use the Lucas, Tooth, and Price 1961 equation, which is essentially brute force statistics. We're using simple linear regressions, or multilinear regressions as the case may be, to articulate variation, rather than using raw physical parameters. We do this because using a statistical approach, we don't just get an answer that is accurate, but we can also phrase uncertainty in a quantitative manner. Thus, you get a plus or minus error line that is pretty representative of the sample. First, think back to college algebra, y equals mx plus b, where y is our dependent variable, x is our independent variable, m is our slope, and b is the intercept. The Lucas, Tooth, and Price equation is quite similar to this. Here you see one iteration, in which Ci represents the concentrate of a given element in a sample in either weight percent or parts per million. R0 is the intercept or constant. Ri is the slope, and capital I is the number of photons. You see the sigma sign, Greek, which stands for sum, and then in parentheses Rin and In. This is the introduction of another element's variation into this equation. It's essentially y equals mx plus b with a little bit of elaboration. In this case, weight percent or part per million concentrations are our dependent variable, and photon counts are our independent variable. Now the way this works is we can use elements that have peak overlaps or key matrix effects to help quantify other elements. This results in a higher quality data set. Here's a quick example of such a quantification. Here we see zirconium gross photons on the x-axis, ranging from 0 to 180,000 photons. On the y-axis, we have zirconium in parts per million, from 0 to 4,000. Up in the top center, you can see the performance of this particular regression. Y equals 0.0163x minus 71. We can read this as Y, or zirconium in parts per million, equals 0.0163 times the number of zirconium photons minus 71 parts per million. In this case, the R-squared value, 0.9768, or for short 0.98, is quite good. Interpreted in a quantitative way, this would state that about 98% of the variation in the y-axis is explained by the x. That is to say, 98% of the variation in zirconium in parts per million is explained by the photon height, by the peak heights in our spectrum. At first glance, this is good, but I'd like to ask you, would you use this quantification? Take a close look at that line. Is this something you'd want to rely on? The observant scientists would note that we've got one value with an x-axis value of 180,000 and a y-axis of about 3,000 parts per million. That is a bit of an outlier, and you can see that it has a lot of leverage. It is dragging the slope of that line up. As a consequence, almost all values between 45,000 and 90,000 photons, or 500 to 1,000 parts per million, would be systematically overestimated because of this high leverage point. This would introduce systematic error, which, while it could be corrected via another parameter, it would be better to tailor the data a little bit better. So in this case, we could remove that far data point and limit our line to get a better calibration. But sometimes we don't want to do that. We'd rather accept a higher variance rate. Why is that? Well, it comes down to statistical validity. While that high outlier point adds significantly more error in the accuracy, it does nonetheless still result in a valid concentration, provided we express that uncertainty. To think about the validity issue, let's think of a hypothetical point, one that is much further out there. You see the little red plus sign far to the right and to the upper right. In this case, we have something that falls outside our calibration curve. Can we continue our line to meet that point? The answer is no, we cannot. While we would get an answer, and it may be close to the right answer, what we lose is the ability to express uncertainty. Our uncertainty past our maximum data point approaches 100% pretty quickly. And also, we don't know if this line would look like this past that data point. Perhaps it's a curvilinear relationship between the photons and the concentrations. It depends on the matrix and a whole other host of factors. All this is to say that the key point is that your reference standards should capture the variation of yours expected in your samples. Another way to think about this is to return to the example of the spectral peaks of the Chinese porcelain. Look again at manganese. Do you see that one red peak height that goes higher than all the others? That is the highest concentration for manganese in this reference set. If we tried to apply it to the Chinese porcelain, we would quickly find that the Chinese porcelain falls outside the range of variation for this particular element. As a consequence, we don't know what our uncertainty is, and thus we don't have a scientific answer. So it's important to note that the concentration data is only valid if we've captured the minimum and maximum with our reference set. It's also important to remember we've got to do this with all elements, not just one. Here, for example, is the reference set used for our mudrock calibrations. The values that are accurate and that have quantifiable uncertainty must follow between minimum and maximum points along these lines. So now we come to the rules for quantifying results. Rule number 1. You must measure with the same parameters as your reference spectrum. In this case, you want to use the same energy, the same current, the same filter, and the same atmosphere. You want to capture the same conditions for an accurate answer. The second rule, you must be within the minimum and maximum of every element in your reference spectra. This one bears repeating. you must be within the minimum and maximum of every element in the reference spectrum. So for example, if you have a sample that has twice as much lead, not only is that lead going to be difficult to quantify, but any spectral overlaps with that lead, or any effects that lead has on the fluorescence of other elements, will also be unaccounted for, which means we have variation that cannot be addressed. This kind of situation can quickly spin out of control. If you have a brand new element, like germanium, that's even in small concentrations, you will still technically be violating your quantification method. So you want to make very sure you've got all the elements correct. The final rule, you must use similar matrix types for samples and reference standards. That is to say, if you're going to quantify obsidian, use obsidian reference standards. If you're going to quantify soil, use soil reference standards. And if you're going to quantify metals, use metal reference standards. The reason for this is depth of measurement. Up in the upper right, you can see an equation, I over I0 equals E raised to negative mu over rho times x. In this case, I represents the photons returning from your sample of a given energy. I0 represents the initial quantity of those photons sent in. Negative mu over rho is the mass attenuation coefficient in a given matrix, and x is the density of that matrix. You can look up negative mu over rho at nist.gov for multiple sample types. Here I've plotted out the values for a borosilicate, the deepest we would likely measure in a given silicate. On the x-axis we have energy from 0 to 40 keV, and on the y-axis we have penetration depth from 0 to 4 centimeters. This assumes only 1% of photons return from our sample. Silica, which fluoresces at 1.7 keV, would be extremely superficial analysis. Lead, which fluoresces at 10.5 keV, we would measure maybe a fraction of a millimeter. Silver, which fluoresces near 20 keV, we could measure up to a centimeter deep in our sample. And barium, which fluoresces at 32 keV, well, in this case, we could be measuring 3 to 4 centimeters deep. Which begs an important question. How we must have reference standards that are similarly thick to our sample. Here, for example, we can look at this in a much more straightforward manner. Look at sodium. With sodium fluorescing at 1.04 keV, the analytical depth is 0.0007 centimeters, or, phrased another way, 7 microns deep. This is extremely shallow. However, if we include zirconium at the bottom, which fluoresces at 15.78 keV, well, the analytical depth there is 0.38 centimeters, or almost 4 millimeters deep. In this case, we would be analyzing quite a bit deeper. This raises an important issue. Your reference standards need to be what we would call infinitely thick. This is to say that they are infinitely thick from the perspective of the photons you're quantifying. So, for example, if you're quantifying barium, your reference standard should be at least 4 centimeters thick. If you're quantifying elements like zirconium or rubidium, it can be a fair bit smaller. I think the safe thickness is something close to 3 centimeters. This way you can quantify your data as well. Your samples have the same limitation. If you're analyzing a thin obsidian blade that is only 0.5 millimeter thick, then you are guaranteed to have distortion in almost all the heavier elements, including lead, zinc, and zirconium. So it's important. Typically, X-ray quantification follows one of two steps. It is to have every sample be uniformly thin, or every sample be uniformly thick. Laboratory and benchtop systems typically require sample preparation in the form of fused beads. This does two things. It creates a matrix of the same type, which means measurement depth is the same, and it makes all samples the same thickness, meaning they're appropriate to that quantification method. However, if we're measuring a soil profile or artifacts that cannot be destroyed, then it's time to think of infinite thickness. If you have some samples that are too thin, I don't want to discourage you from analyzing them, but be aware that there are certain physical limitations to how we can quantify that data, and you will be running right up against those. Here is a similar profile, but this time for a lead glass. Here you see the same x-axis, 0 to 40 keV, but our y-axis this time is 0 to 0.04 centimeters deep. So for lead glass, infinite thickness is less than half a millimeter, whereas for a regular silicate, it was upwards of 4 centimeters. This is why having the right matrix is important. If you're going to quantify lead glass, that is fine, but make sure you use lead glass standards. Likewise, if you're going to quantify a silicate, use silicate standards. Once you follow those rules, you're in a position to be able to do elegant quantitative analysis. Here, for example, is a geologic core measured with the tracer, where we see calcium and molybdenum. Here, we can interpret clear changes over the record of these two geologic cores, and we can interpret them in a quantitative sense. It is possible to do quantitative analysis, but you must make sure you follow the rules for quantification. And remember, rule number 1, your spectrum must be taken with the same parameters: energy, current, filter, and atmosphere. Second, your reference set must be within the minimum and maximum of every element that you expect in your sample. And finally, make sure you're using samples of the same matrix as your sample to quantify them. Thank you very much. If you have any questions, please don't hesitate to let us know.